Hi everyone. In this video, we'll do some more examples relating to rational functions, taking into account all the methods you've learned in this course. In the previous video, I suggested that you always follow a certain priority system when it comes to integrating rational functions, so let's just recap that. First, check if the fraction is proper. If it's not, then perform long division to end up with a result that is proper. And once you have a proper fraction, then you should check for an easy u substitution. This could include integrals of the form f prime over f, for example, but other u substitutions might also be possible depending on the function that you've been given. If you can't find any easy u substitution, then the next thing you should do is look for a sum or difference of squares, keeping in mind that they might be disguised as a quadratic function through the process of completing the square. If you can find a sum or difference of squares, then you might be able to make use of inverse trig or hyperbolic formulas, or perhaps even a trigonometric substitution. And if all of the above fails, as a last resort, you can always try to find a partial fractions decomposition. Once you have that, then you'll find that each of the partial fractions can be dealt with using this same system of priorities. So just repeat this process on each of the partial fractions and you'll be good to go. Let's practice some more examples. Try this one on your own, and when you're ready, let's continue. First note that this is a proper fraction, so there's no need to perform long division here. So next, we look for an easy u substitution. Notice this x in the numerator looks very much like the derivative of x squared plus 1 that we see in the denominator, and this strongly suggests that a u substitution could work. The derivative of x squared plus 1 is actually 2x, so it would be more ideal if we had a 2x in our numerator, but we can make that happen provided we also cancel the 2 with a 1/2 out front. Now, since the derivative of x squared plus 1 appears as a factor in our integral, this would make a good choice of u. Because sure enough, du would then be equivalent to 2x dx that we see in our numerator. Putting this all together, we end up with 1/2 of the integral of 1 over u squared du, which is easy to calculate. Just express this as u to the minus 2, then apply the power rule and you're finished. In this example, an easy u substitution was all we needed, but you'll notice this example does also contain a sum of squares, which could have led you down the path of trigonometric substitution if you wanted, and that would have worked, but I think it would have been substantially less efficient, which is why I don't suggest looking for sums and differences of squares until trying easier methods first. Let's use this same system of priorities to attempt another example. Again, pause and try for yourself, and when you're ready to see the answer, let's continue. First, notice this is an improper fraction, so as a first step, we must perform long division. Start with a setup as you see here, then divide the highest power term in the dividend by the highest power term in the divisor. In this case, we're dividing 2x cubed by 2x squared, and the result of that is x, so we record that where you see here. We see that we want to subtract x groups of the divisor, so multiply the divisor by x, and then subtract the result. You can pause and check that x minus 3 is what remains after subtracting. And since x minus 3 is of a smaller degree than the divisor, we can stop dividing here and interpret these results. We see that the fraction we've been given is equal to x plus the remainder, which still hasn't been divided, so that remainder remains over top of this denominator. Now, x is easy to antidifferentiate, so we might as well do that now. But we're still left with the integral of this rational function, which is now proper. So let's look ahead to our second priority. Check for an easy u substitution. Our integral here is not of the form f prime over f, and there isn't any other u substitutions staring us in the face. You can pause and think about that if you like. So let's look to our third priority. Check for a sum or difference of squares. We can get one of those by completing the square, since our denominator here is a quadratic expression. So let's work through the details of completing the square together. First, we form a set of brackets for grouping the first two terms, leaving the constant term outside. And notice our x squared has a visible coefficient of 2, so we need to factor that out of the first two terms, as I've just done there. After that, we look at the coefficient of x, which is now -2. If we divide -2 by 2 and then square the result, we get +1. So we add +1 inside our brackets, and since it's inside the brackets, the +1 we just added is also getting multiplied by this 2. So to correct the change we just made, we need to subtract 2 outside the brackets. Now we can factor our brackets to obtain the sum of squares that we wanted. Now that we've got our sum of squares, we can start looking to inverse trig or inverse hyperbolic formulas. You could also think about trigonometric substitution at this point, but since that method is quite technical, I don't recommend it unless you're completely out of other ideas. In this case, our denominator is shaping up to look like u squared plus a squared, which should remind you of the formula for arctan. And to make that structure more clear, we're motivated to make the substitution u equals x minus 1. In that case, du is the same thing as dx, making for a pretty clean substitution. So with that, we get 2u squared plus 9 in our denominator, but we still have this x in our numerator. For that, we need to go back to our substitution and check what x is equal to. In this case, it's equal to u plus 1. So where we see an x, we can put u plus 1 instead. And then after simplifying, we get u minus 2 as our numerator. Now, keep in mind that this substitution was made with a view towards trying to use the arctan formula. But that formula requires our numerator to be constant. The chunk I just circled looks like it could be made into arctan, which motivates us to split up our fraction into two terms at this stage. Our first term would have a numerator of u, and our second term would have a numerator of -2, which you could pull out front of the integral as I've just done here. Notice that with a slight modification, this first term is now of the form f prime over f. So we can evaluate that as the natural log of the denominator. I've dropped the absolute value here since we know 2u squared plus 9 is already a positive number anyway. As for this last term, we were trying to make it look like arctan. And for that, we can factor out the 2, because that would make the denominator look like u squared plus a squared rather than 2u squared plus a squared. Just be careful that the 2 needs to be factored out from both the terms in the denominator, which makes the second term into a 9 over 2. Now we can cancel the 2 over 2 in front, and we notice the denominator is now of the form u squared plus a squared, where in this case, a would be 3 over root 2. So check your formula sheet to see that this evaluates to the arctan expression that you see now. So we finally come up with this answer. But as a final step, don't forget to express it back in terms of x. Hopefully, looking at a few examples, you're reasonably convinced that this priority system I suggested works well. But as you can see, things can still get pretty complicated when you're working with rational functions. So make sure to do lots of practice. You can even make up examples of your own rational functions if you want, because literally the only rational functions that you would have trouble anti-differentiating at this point are ones where the denominator can't be factored easily, mainly because that would present an obstacle if you needed to resort to partial fractions. But with that, I'll wrap up the video here and see you next time.